I'm going to go, as soon as my mouse allows here, into the beginning of the solar wind. One of the earliest indicators of why there is a solar wind actually came from looking at comets. And we'll get back to comets sometime later this week because they're very interesting objects in themselves and as tracers of the solar wind. People had known for some time that comets often have two tails. One tail, we now understand, is formed by dust falling off the comet as it heats up in the sunlight, being blown away by radiation pressure, literally just photons bouncing off of them. And I think it was Biermann in Germany in the late 1940s who said, that tail, there's a second tail there. And in this particular one, it's very bright, a nice bright blue tail. That tail stands away from the sun so directly that photons just can't give it enough pressure to make that happen. Something else has to be happening. Now, this was also just after the time that people started seeing these iron lines and recognized them for what they were. It took a while for people to see iron lines from ions that have 22, 23, 24 of their electrons removed to recognize that as a spectrum from something that exists on Earth pretty commonly as of iron. But once they realized that, they had to figure out, this is really hot stuff. And if it's that hot, it isn't really bound very efficiently anymore. So maybe that's what's streaming away and part of it. It took them a while to figure that one out. They thought at first, well, maybe it's only occasionally when these flares go off that particles stream away from the sun and actually cause these second comet tails. But then, of course, just about every comet you look at if it had a second tail, pointing straight away from the sun. So they realized very quickly it had to be a continuous streaming out from the sun. And this is where people like Gene Parker started earning their reputation. He wrote them all. He actually wrote down the equation and said, well, look, it can't do anything but flow out, no matter what you think. And he did get it published, and after that everybody believed him forevermore about whatever he wrote down. He's a very good, very insightful guy. Why is there a solar wind? If you had to say it in sort of one word, you can choose different words, but why is there a solar wind? There has to be a solar wind. The sun cannot just decide not to have a solar wind. It's not the escape velocity. It doesn't, at these temperatures, nothing is moving fast enough that it will just fly off the sun. Gravity on the sun is pretty strong. Something is pushing it off. It's the gas pressure. It's the gas pressure, but if you start pushing material off, starting at 2-3 million degrees, and you push material into space, now you're dropping it from, what was it, 10 to the 14 particles per cubic centimeter in the corona, to how much is it in the wind? I'll show you the table in a moment. What's the particle density in the wind near Earth? 10. So you go down 13 orders of magnitude. You expand the material by 13 orders of magnitude. Is not going to be 1 million degrees anymore unless you get energy into it. Now, one way to get energy into it a long way away has to do with magnetic field perturbations. And yes, they do push. But that's not the primary reason for the solar wind to flow out. It's the electrons. The electrons are really, really efficient in conducting energy. So they keep the plasma hot, far, far out. And because they keep it hot, it maintains its pressure, and it can keep pushing. So it's just because it starts hot, and it's so tenuous that these electrons just go fly out and occasionally far out interact with the ions to heat them up, that they maintain the pressure to flow out. I'm done. But I'll show you some of the more intricate processes on this. Now, there's roughly, people like to think in terms of this as two types of wind. There's something they call the slow wind, which is a mere 400 kilometers a second, and the fast wind, which is a mere 800 kilometers a second, more or less. Of course, that's in case the solar wind is unperturbed, and it pretty much never is unperturbed. There are other things running through that have to do with the coronal mass ejections that I'll get to later on. But there is a tendency for the wind to divide into these two categories, a slow wind and a fast wind. And they have slightly different densities and slightly different velocities. Curiously, their product, the momentum, is pretty much the same at all times. So it all pushes it about the same way, away from the sun. The densities, as I said, are really low. They're of order 10 or 3, depending on the wind that you look at, particles per cubic centimeter. And this is one of these transformation things that you have to do. I can't think in terms of Teslas, even though I was trained in Teslas. I think in Gauss. The magnetic field is 1/10 of a Gauss, more or less. So what did we start from? In the photosphere, boy, can you remember that number? From the photosphere. Those people that are trying to model the solar wind starting from the surface of the sun go over 22 orders of magnitude in density. This is a slightly non-trivial exercise. This is one of the reasons it's so difficult to do this. The magnetic field goes down by 4 orders of magnitude, from a few kilogauss to 1/10 of a Gauss. And the speed obviously goes from hardly streaming anywhere. The solar atmosphere is pretty much everywhere stratified according to its temperature. If you could look at a coronal hole out of which the solar wind flows, the stratification would be pretty much that of a stationary atmosphere. There's just this very slight push-off that then rapidly, ever more rapidly accelerates as it pushes off from the wind, from the solar surface. Now, I've put these in mainly to remind myself. I'd like you to go back to Volume 1, Chapter 9. Viggo Hanstein wrote this chapter. He did this for his thesis work. And he basically did the following experiment. You don't have to even look at the diagram, just listen to my voice. There's 2 diagrams in here. One says, what if I had a magnetic environment like this coming up from the sun and it just had a hard top? And I put energy into it, what would happen to that energy? Well, that energy is going to be redistributed. There's a cold plate at the bottom. It's going to get conducted down. The thing that conducts most efficiently is the electron. So at some point, the electron temperature is going to drop. Wherever the collisions are frequent enough with the ions that it can maintain that exchange of energy, the temperature of the electrons and the ions are going to be the same. But if I make my tube high enough, at some point, the collisions are just going to not be frequent enough anymore. The electron temperature will go down because it's depositing its energy lower down from where it's radiated. The ions go, where did you all go? I'm still up here with this energy. So they remain at a much higher temperature. And then we take the lid off. And now the wind flows because it has to. One of the exercises there is to show why it just has to. If it's hot, it cannot but flow. But now you're removing energy on 2 sides. You're dumping energy at the cold plate at the bottom, what we call the transition region in the chromosphere, from where it radiates, and the lower part of the corona. And you're drawing out matter at the top. The electrons are pushing energy in both directions, so their temperature is going to drop even more. And even in this case, now the ions get the idea too. Like they're flowing out, they're expanding, and their temperature too is dropping. At the same amount of energy input, the radiation differs substantially. The radiation scales as density squared. Why does it scale with density squared? What is it that radiates? The iron and the carbon, the nitrogen, the oxygen, all these ions. You need to collide with the ions to radiate. So it's at least proportional to the population density of the ion and the collision frequency, and that's the electron density. But because the electrons all come from hydrogen, most of them, it's really the same density. So we can just write down density squared. Density squared determines how bright the corona is. So now look at the densities here. The closed structure has a density of order 10 to the 7, 10 to the 8, more or less high off the sun. This one goes down to 10 to the 5, maybe 10 to the 7 at the base. So from 10 to the 7 to 10 to the 5, it dropped by a factor of 100. 2.5 solar radii off, 1.5 solar radii above the surface. Factor of 100 in density, factor of 10,000 in brightness. No wonder that wherever there's wind, the corona goes dark. It's the same energy, pretty much, give or take. I'm sorry, I'm an astrophysicist, give or take an order of magnitude. But the brightness is very, very, very different. And that's why they're called coronal holes. People looked at these things in the very earliest X-ray images and like, there's a hole. They said it in German. But the term stuck. It was translated, and everybody calls these things coronal holes. So they're holes only because they're dropped in intensity. Yes?
You just said about the electrons' temperature decreasing, and in that time you
high up, they differ. Low in the corona, in the pictures I showed you in the first half, the temperatures are pretty much equal, except during impulsive phases when all the temperatures either have no meaning at all or they can actually decouple. Low in the corona, they're the same. High in the wind, the ion and electron temperatures are generally very different. Now, you can make life even more difficult on yourselves. I won't do it. I'll just describe it to you. In many ways, the solar wind is a multi-fluid plasma. It's not the simple coupled electron-proton plasma. These particle populations do as they please, more or less. There's couplings, but they're weaker. The further out you go, the weaker the couplings become. And in fact, we can't even, although we often describe things by a temperature, the temperature itself becomes direction dependent because it makes a difference whether you measure random kinetic motions along the magnetic field or random kinetic motions parallel to the magnetic field. You should be aware of this. It's not part of the story that I'm going to tell here. That would be too long to tell. Essentially, what happens is this. If I put energy into the corona and it becomes hot enough, then at some height, the pressure in the gas is going to exceed the force that the magnetic field can contain it with. It's going to literally disrupt the magnetic field and blow it out. And it's going to go radially out. And if you look at a picture of a solar eclipse, these stalks that you see coming out everywhere, but in different patterns and different intensities, are essentially magnetic field being dragged out and matter streaming out, preferentially in some places over others. And wherever the density is higher, you get this higher intensity light, because that light, by the way, is visible light. What light is that? This is not iron glowing. What's glowing in these kinds of pictures? Which charged particles particularly? It's electron scattering of white light. This is really bright photosphere underneath, shines out light, the light hits some electron somewhere, and that light comes to us and creates these nice pictures if we point the right kind of telescope at it at the right time. I want you to see two distances in a diagram like this. By the time you reach about 2.5 solar radii, pretty much everything is already open, and it's very nearly radially open already. Most modelers and most models that I'll show you from here on out that don't want to model the entire interaction say, I'm going to simplify life. I'm just going to make my field go radial at 2.5 solar radii. Typically, that's what people mean when they say, I'm using a potential field source surface model. Because if you put a source surface somewhere that has mirror charges, you can look this up in Jackson, if Jackson is still around, then you can counter everything so that the boundary condition at 2.5 solar radii is so that all of the field actually becomes radial. And typically, people call that surface the source surface, which it isn't. This real source surface is at the square of that distance. It's at 6.25, but in between, at that distance, everything becomes radial. So you can call it source surface if you wish. Just keep in mind that the actual mathematical trick puts the mirror surface, the mirror charges at about 6.25 solar radii. Then there's 10 solar radii. 10 solar radii is the distance at which the wind is so fast and the field so weak that you've reached the point where we're no longer really the sun. The velocities are super-alphanic and supersonic. There's no signal going back. At that point, you're in the heliosphere proper, 10, 15, 20 solar radii. Partly, we don't know. Partly, it varies depending on the phase of the cycle that you're looking at. Okay? So those are the two key distances. Now, the bottom part of it is being driven by this ever-changing magnetic field. And I'm just showing you one particular incarnation to drive home the problem. We have a ball that's 1,000,000 times the volume of the sun, of the Earth, fitting inside the sun. And from there on, you go at least 2.5 more solar radii before the field is actually being pushed open. That's another 6 million balls of Earth that we have to all model in our MHD models if we wanted to do this from scratch properly. So we can't do that. People make approximations. They either say, well, it is mostly potential, and if things aren't exploding, that's a pretty good approximation, actually. If things are exploding or rapidly evolving, you'd like to do a full MHD model, but nobody can drive a full MHD model at the required resolution to do it over a long enough period that you can build up all the stresses in the electrical currents. So people do an MHD-lite One of these models is magnetofrictional, in which you basically say that, well, I know the Lorentz force is acting on something, but I'll pretend it's acting on syrup. There's some viscosity that slows the motion. Like it gives it a fake inertia. It isn't just going, it just gradually drifts in the direction that the force is pointing, and then you keep evolving the model, and this whole model keeps doing this. That is a spinning sphere, evolving rapidly, driving wind into the heliosphere. I have a great deal of respect for people who try to visualize what the solar wind is doing, because it's, to me, a horribly complex system. But there are a few easy pieces to it. One of this is this. The wind pushes the field out radially. How does the field decay as a function of distance from the sun? Y1 over r squared. It's a dipole. It's a dipole field. Shouldn't it go like 1 over r cubed? No, because it's radial. You're absolutely right. It's radial, so it's behaving like a monopole field. So it goes as 1 over r squared. This is one of the arguments people had a long time ago. They go, it's impossible that the solar corona affects us here on Earth because it's a 1 over r cubed field. No, it's a 1 over r square field because it streams out radially. But it streams out radially from a largely dipolar field. Now, this is an interesting one. If you look at the surface field of the sun, I've shown you this movie, is an incredibly complex, highly dynamic structure of multipoles on multipoles in this enormous hierarchy. By the time you get to 2.5 solar radii, it's almost a dipole with some quadrupole and octupole moments on it. It's actually pretty much the same ratio as Sabine was showing this morning that sits between where the Earth's dynamo region ends and we sit at the surface here. So we measure mostly a dipolar field. The solar heliosphere sees mostly a dipolar field. Not quite. And that's where this gets interesting. So now we have this dipole field, one polarity going out on one side, one polarity is going out from the other polar region. At some point they're going to hit two polarities of opposite sign next to each other form I say this out loud. A current sheet. It's the biggest current sheet around that we have access to. And that's a diagram that Alfvén already drew a long time ago and said, look, we have this undulating structure because it's a dipole field with a perfectly symmetrical current sheet on top of which I put quadrupole and octupole moments, so it's beginning to undulate a bit. And now I spin it around at about a 27-day period, which is the average rotation period of the corona as a whole. And then I put the Earth in that. And it means that the Earth is going to be hit by these current sheets every 27 days in a repeating pattern, as long as the pattern on the sun doesn't change too much. That was the first discovery people made. The 27-day recurrence pattern in geomagnetic storms were like, this is interesting. That looks like the sun hitting us. And it is the sun hitting us, okay? Except that on top of that, lots of other things happen. This is my rendering of it. This is taking this flux transport model that I showed you this morning, but now doing something artificial entirely. I'm showing you the sun from a co-rotating perspective. I've got a co-rotating satellite. Wouldn't that be a nice one to have? So I can see the same face of the sun all the time. One thing you see immediately looking at this magnetogram is the differential rotation. Things near the equator go one way, things near higher latitudes go the other way. It's just the differential rotation of the sun, which jumps out at you if you look at it from a co-rotating frame. And then we took all the recipes that the sun gave us, the size distributions of the bipoles, the orientations, the patterns in latitude, and all that, and just said, let's do parent distribution functions modulated over a solar cycle. What happens? You can make a potential field extrapolation, and out of those many field lines that I could have drawn, the ones I'm showing you are the last closed field lines. Well, in this model. So the thick line that you see warping around is the base of the current sheet. From there on out, it's the current sheet. Under it sit the structures of closed field. Those are the helmets that you see sticking out when you look at an eclipse picture, out of which comes the stalk, which is essentially a part of the current sheet. And you can see that this thing, look at the clock, it's about a month per second, evolves very, very gradually. And it does one thing interestingly. It started out almost as a dipole, and then you must have seen it tip and tilt, go almost north-south, and then it went over. And what it's doing is following largely this capacitor function of the poles. The polar caps have a particular north and south polarity that weaken over the cycle, and then suddenly the field of the active regions begins to dominate. But as they grow again, you go back into this simple dipole, except that it's flipped. So it does this dance. It wobbles around, sitting there as almost a dipole, goes over, flips and spins and turns, and comes back to rest now in its inverse position. And it does this every 11 years or thereabouts. Back to the dipole. Yes?
So your source surface, it looks like it's fairly constant distance.
Yes.
Is that set to be a constant number?
In this assumption, in this approximation, we set it fixed to 2.5 solar radii. And the reason we picked 2.5 solar radii is that at that distance, it matches the positions of the coronal holes best in X-ray images, because there we can map them down to the surface, and it maps the streams in the wind out near Earth best. But it does vary, and it is not a simple sphere, and it isn't any other simple ovoid either. It's a very strange undulating sphere that needs to be understood properly. MHD models do better than that, but MHD models are really hard to run for this amount of time and to visualize this easily. So I chose this one, just to give you the feel for what's happening. All right, now, apart from translating Teslas into Gauss, I always have great difficulty in reading these diagrams, and it depends on your preference on how you've been trained. Take that one. This is a run of the density in the wind near the Earth as a function of time. So I see this first, and this comes later, and that comes later. And to me, this puts this diagram in an orientation that I can't think in, because geometrically it's exactly the other way around. So I'm going to show you both. Just pick the one that you like, that you're most comfortable with. To me, this now says, I see spikes in density in the solar wind. Those spikes occur right at the interfaces where the temperature in the wind changes. And go to the next diagram down. They also happen just as the pressure goes up. So I see a spike in density, a raised temperature, a raised pressure, and in fact, if you look at the bottom diagram, even a spike in the magnetic field. So what's happening here? You send out slow wind from part of the solar surface, you send out a fast wind from another part of the solar surface, and you spin the sun underneath it. What happens? At some point, a fast stream is going to go overtake a slower stream ahead of it. It's going to just run into it. And it's going to run into it at a couple of 100 kilometers a second, which is pretty darn fast, even in the terms of the properties of that wind. It's faster than sonic. It's often faster than the characteristic magnetic speeds. So you get these compression regions. And if they are fast enough overtaking, you even get shocks at those points. So it's just wind flowing out radially off a rotating sun. How does that work? Well, I'm going to skip this. I'll get back to that on Monday, okay? I'll show you that a little bit in some detail. Imagine first we have this variable wind. That is to say, different pieces of the sun, different parts of the surface of the sun, send out different velocity streams. And I rotate the sun underneath it, so these streams are going to interfere with each other. And I'm going to start from just this diagram that shows, look at this top diagram, as a function of velocity and distance. I'm showing you at different times, 50 hours, 100 hours, 150 hours away after sending the fast stream into the slow stream ahead of it, what the profiles in velocity would look like. Well, what you see is that fast stream is going to overtake the slow stream. It's going to, in fact, at some point, it's going to start pushing the slow stream. Depends on just how fast it is moving, whether it pushes in a shock or it pushes in a wave. This is slow enough, it pushes in a wave. So the wind ahead of it begins to accelerate too. And you get this compression region, which in the bottom diagram is where you see the pressure, that because of the compression, the pressure goes up in that interaction region. And because this faster stream is streaming ahead of slower stuff behind it, the pressure drops behind it. So I got this pulse in pressure.
Of course, there will be many instabilities out will be out of trigger and Y1 instability and things like that.
I'm just giving you the simple story to start with, okay? And then here is the picture, what happens if you think of this in the full geometry of what happens. That the wind stream isn't sent out at any one time. Most of those streams persist for a very long time on this rotating pattern. So as it happens then, is that if you look in the direction where you've just sent out the streams, there's a fast stream interacting with a slow stream here, creating that that increased density and high pressure region. And as I look at different directions, I look ever further into the past. So that stream further away has had more time to interact, but it's also come into a region of the heliosphere where the properties of the medium have changed. The densities dropped, the fields dropped, the temperatures are changing. And what this does is at some point far enough away from the sun, typically beyond Earth orbit, those interactions of streams become shock fronts. And you can have shocks run now forward and backwards away from that interface region, the dashed line in the middle. I should use another pointer. So this is the interface where the fast and the slow stream are interacting, but here are these shock waves running away. Now these shock waves do things, I don't know if we actually get to it in terms of, this one seems to work fairly well, right? No, I don't see where it is. I see. Okay, we've got our lightsabers here. These things are important in that they are shocks and they actually create energetic particles that are part of the reason why energetic particles can stream from the sun to us, but even from beyond us, backwards, because they come out of these shocks. This particular pattern.
It does work.
Would you like me to use both? This particular pattern still sits on this rotating sun. So if you look at this in terms of time, what are you going to see? What is this pattern going to do? The pattern's going to spiral. The pattern will spiral. This is why it's called a co-rotating interacting region. It's co-rotating with the sun. So there goes the spiral. What's the direction of the solar wind that sits in it? Where's the wind going? It's going along the spiral. It is the spiral. I don't know how many of you have seen these old-fashioned garden sprinklers that spin, but they form these beautiful spiral patterns, and every drop, just stand in it, every drop goes straight out. Except not quite everywhere. Okay? The co-rotating interaction regions are where the field is not co-rotating, and the non-co-rotating interaction regions is the region where it is co-rotating. This is horribly confusing, but that's when different cultures, different disciplines start talking different languages and then suddenly talk to each other. The solar magnetic field close to the sun is strong enough that it resists distortion by the presence of the nascent solar wind. The wind is just going to flow with the field. At some point, the field becomes so weak that it can't stop the motion of the particles anymore. At that point, the wind flows out, as I guess Newton or maybe even Galileo started thinking about. Things go in straight lines from that point onward. So where it goes out in a straight line, it forms these co-rotating interaction regions. Close to the sun, within about an Alfvén radius, so within that volume that I showed you before, the 10 solar radii out, the solar magnetic field basically says, this is my shape, and I'm going to rotate with the sun as it is. And that brings me to the very last thing that's going to go away from the sun with that. Because of that action, the sun is actually losing angular momentum. And it's slowing down over time on a time scale that by now is sort of 1 billion years before it rotates down by a factor of 2 or thereabouts. When the field is stronger, the wind is stronger and the field is stronger, the Alfvén radius is further out, the mass flowing out is stronger. When the sun was young, it spun down pretty quickly. It took tens of millions of years, with an M, before the sun spun down from about a day rotation period to maybe 5 days of rotation period. After that, it slowed down its angular momentum loss. Matter flows from the sun, which is rotating. So clearly that matter takes angular momentum. Does that slow down the sun? If I have a spinning sphere and I took off something from its surface, I've got angular momentum right here in my hands. Has the sphere slowed down? No. What I've done is taken the specific angular momentum of that piece of material, and I've now got it in my hands. Well, I've slowed it down, so I've caught the momentum in my own hand. But the sphere's angular momentum hasn't changed. So moving the wind off the solar surface does not slow down the sun. What does? It is the magnetic field. And why does it do that?
It accelerates the solar wind or distance of several solar radii in the direction of solar rotation.
Okay, yes, I think you said it. You said it right, but I tend to think about it differently. Yes. Basically, I've got rigid arms sticking out from the surface out to 10 solar radii. And over that distance, the angular momentum is actually, as the wind flows out along that field, it's got to increase its angular momentum. The field is actually exerting a torque on the wind until it lets go, 10 solar radii out. And because I've now taken angular momentum not just from the surface, but from 10 or 15 solar radii out, I've taken 10 or 15 times the amount of angular momentum from the matter leaving the sun. So I am applying an air brake, a magnetic brake, to the sun that way. So, can we put that together? Yeah, there's one more thing. Things explode. And this is really neat to look at.
So before you get to the
Yes.
explosion, can I just do a Gedanken experiment with this idea of angular momentum going away? So if you had your idea of a mass leaving, carrying angular momentum, but leaving the specific angular momentum of the sun, so the angular momentum per unit mass to be the same, right? So just the particles. So if you then had the sun in vacuum without a magnetic field, it would just keep spinning the same amount, no change in spin.
Right.
Okay. But now what if you took the magnetic field and you had it going out into vacuum? You could still be sending out the photons, but say there's no plasma out there. I'm just trying to do the experiment. Would you then, you would not actually have it slowing down? You wouldn't
It's
have
not in a
it
vacuum magnetic
Right.
field, no.
So if you didn't have the solar wind leaving,
No, you have to have both.
and you just had the magnetic field out there,
If you could devise a way to uncouple it, if you flew out a neutral wind that didn't couple to the magnetic field, it wouldn't carry more than its own angular momentum. It would fly out radially immediately. It's the arm of the magnetic field that causes it to steal angular momentum from matter lower down.
but if you decoupled the sun from the material out there, so say you had the alpine travel time was long, you couldn't get alpine waves out there, how would the sun know that there's material out there slowing it down? Maybe we should
Okay, you're mixing a number of concepts, at least in my mind. I don't need to have alphane waves go anywhere to push the wind out, right? The pressure does it all, the gas pressure does it all by itself.
Yeah.
But as long as the time it takes for matter to move is short enough for it to tell, I'm stuck to this field line that's coupled on the surface, it is linked to the surface. And it begins to break down, not at the alphane radius like that. It's a gradual process. But it's equivalent to, if you write down the equation, I can show you the equations that I didn't come up with, but other people did. It is equivalent to the distance of the alphane radius, even though it's a very gradual process. Let's get back to that as questions. I'd like to finish with this, because this is basically, oh, why did it stop? It's such a nice movie. Because it didn't start. Okay, there. In all of this that I've been describing thus far, we throw out coronal mass ejections. And coronal mass ejection essentially are flux ropes moving out and expanding as they do so. They move typically faster than the solar wind, but not always. This is a case in which it moves so much faster that it actually forms a shock compression front ahead of it. And that shock, now you're looking down on the ecliptic, seeing the sun spin, seeing that beginning of that, what's called the Parker spiral, of the outflowing wind that's moving radially, into which we throw coronal mass ejections. And this is a simulation that's probably akin to what happened when Carrington and Hodgson, both of them, saw that very first flare, because Carrington also noticed Kew Gardens was just a few miles down the road. Kew Gardens had a magnetometer, and they noticed this magnetic signal. Now, this is curious. Why is that changing? Somebody else will explain that. That's not the geomagnetic storm. But they figured because of that, that somehow there had to be a connection between the sun and the Earth. A few days after that, there was a huge geomagnetic storm. And current modeling says that maybe that wasn't just one coronal mass ejection going off, but it probably was a region that's just flared a whole series of times, as we've seen in like 2003, when the sun was rotating and it was shooting off coronal mass ejections in all directions, and spacecraft saw it literally from out where the Voyagers were to the inner planets, just in any direction because something was going out, that these shock waves can plow up into each other. One catches up into the evacuated space behind another, moves a little faster, they merge, and these joint shock waves might mean that you get these really strong geomagnetic storms from composites of flares. So this is another warning that I'm putting into here, that not all one metric, one measurement of a characteristic, like there was a flare of that magnitude, means that you can map it into any other metric, because you can have wavelength changes or you can have multiple effects pile up in a series. But that is essentially what's going to hit the Earth's magnetic field and anybody else's magnetic field and form all this geomagnetic activity, which we'll talk about after Sunday. Questions? I'm going to stop. But do you have any questions?
Yeah, you showed the two state of solar wind last time. Their slow solar wind had the less temperature, photon temperature is less than the fast solar wind, but the plant temperature is higher for the slow solar wind. What is the explanation?
That's not something you should ask me. The origin of the fast streams is fairly straightforwardly understood, as this is where all of the coronal field, almost all of the coronal field, is essentially blown open into the heliosphere, and it stays that way. The slower solar wind somehow comes from the interaction and the exchanges with the closed magnetic fields under it that somehow temporarily seem to open up. This changes the composition, the elemental composition, it changes the ionization balance, it changes the anisotropies in the medium. So that's not something I think I can explain, and certainly not in 2 minutes here. That's more than a few PhD theses together. Any other question?
Would you
Sorry.
In that model you showed where you were mapping out the last closed field line, there were some points where you could have like two hemispheres.
Yes. It's a multipolar field that's being blown open. So yes, at some point you can create these things. There are cases where we see multiple crossings that suggest that, particularly at higher latitudes, that there are also current sheets. But you would also have seen that it's rare. Even in that simple model, it doesn't happen all that often that you see a second current sheet. It mostly is one. That's not too dissimilar from what's really happening as far as people measure the heliosphere. I'm beginning to realize that there's that one image that I'm going to discuss on Monday with you, because that's the image now that you should be able to explain after all this introduction. So look at that one. Maybe I'll pick the questions. Maybe I'll pick this image to talk about. We've got all of tomorrow.
could have a truly metal synchronous satellite at 40 yards, what science could you use as now?
One of the reasons why NASA and ESA in particular are considering the solar orbiter is that the solar orbiter is going to go into a highly eccentric orbit, which at least for a month or so at a time will put it in near co-rotation so that we can actually see the magnetic field evolve. What I said at the beginning was that the time scale for a typical active region to evolve is of order a solar rotation. So we can never track it from beginning to end. And this would be one of the cases that we can. Plus, if we do reach that near co-rotation, then at least we're doing what you were describing this morning, talking about multiple spacecraft. The problem of the thing is moving and your spacecraft is moving. So if you can freeze the rotation of the sun, at least that confusion temporarily by co-rotating in the perihelion phase of your orbit, you can take that out of the equation to a large extent. So you'll be looking at something underneath for a considerable amount of time as the whole field is reconfiguring, but not also sweeping by your spacecraft. 15 solar radii, is that about right? 10, it now goes to 10, okay. In the back, Madhulika Gauhartakota joined us. She's the program scientist at NASA headquarters for Living with a Star, and she's funding all of you. So say hello if you can. Any other questions? All right, let's take a break.